This is the GCSE Physics paper from CCEA, Unit 1 in June 2015. We're going to have a walkthrough of the questions. Let's get started. Question 1a. To investigate the motion of a ball falling from rest, a series of photographs were taken at regular intervals. The diagram on the right was copied from the photographs obtained. So, we've got this ball, and at regular time intervals its photograph is taken, and you can see its position is changing as the time goes on. Describe the motion of the ball and explain how the diagram supports your answer. Well, what we should be able to notice here is that the first time period it went a small amount, and that increased and increased and increased. So the distance covered in each time period is increasing, and that means this ball is accelerating. And that's really what you want to explain. The ball is accelerating because the distance covered in each successive time interval is increasing. Part 2 then, it says each photograph is taken 0.1 of a second apart. Using the diagram, calculate the average velocity of the ball when it has fallen 1.2 meters from rest. Do not assume a value for the acceleration due to gravity in your answer. Okay, so we're told that each one of these is 0.1 of a second. So each one of these intervals represents 0.1 of a second. So 0.1, 0.1, 0.1, 0.1, 0.1. So there are 1, 2, 3, 4, 5 intervals. So this whole thing represents half a second. Now you can add those in by scribbling them in to the gaps here. But we've got a total time of half a second and a total falling distance of 1.2 meters, and that's allowing us then to get a average velocity, because average velocity is total distance travelled over total time taken. So we need to divide the total distance of 1.2 meters by the total time, which is half a second, and that's going to give us 2.4 meters per second. So you want to give some kind of formula, numbers going in correctly, and your answer. Part 3 then, using the equation below and your answer to part 2, calculate the final velocity of the ball when it has fallen 1.2 meters. Okay, so we've got initial velocity, final velocity. The average velocity can also be written as the mean of these two, and we do know the value of one of them. We do know that it starts from rest, and we do know that we're interested in a final velocity here. And we do know from our previous calculation that this is 2.4. So you're basically just substituting into that. So you've got V average equals U plus V over 2. And 2 times V average equals U plus V. And we know that U equals 0, so we can take U out of it. So in our case, 2 times V average will equal V, the final velocity. So V must be 4.8 then. Okay, part 4, calculate the acceleration of the ball as it falls. You're advised to show clearly how you get your answer. Well, remember that A is like V minus U over T. So, we know it started at 0, we know it reached 4.8, and we know that took half a second. So we've got like 4.8 over 0.5, so we've got like 2 times 4.8, which is going to be like 9.6. And that's that. Part B, some of the data from the series of photographs is plotted on the grid below. S is the distance fallen in millimeters, and T is the time in seconds. And so you can see we've got a curve here. Complete the graph by drawing either a curve or a straight line by deciding which one best fits the data point. So it's quite clearly a curve. Okay. Now, to be totally honest, it took me about 15 goes on the iPad to get a curve here that I was happy with, but this one will do. When you're plotting something, you really want to get your hand round to this side, so turn your paper around so that the natural curvature of the movement of your hand matches the curve that you're trying to draw. You shouldn't really try and draw this from down in this zone with your hand here. Put your hand up here by turning the paper round, and you should find that your hand is much more able to follow the curve. The relationship between the distance fallen s and the time t is given by the equation s equals kt squared, where k is a constant. Using values taken from the graph you have drawn, calculate the value of k. You're advised to show clearly how you get your answer. Okay, so s is equal to k times t squared. So what you're going to want here is a value somewhere on your graph line that you can read easily an accurate value of s and t, and then you square t, and k is going to be s over t squared. So you're going to look at your graph and find some suitable values of s and t squared for those. So I'm taking these last values, 1200 millimeters fallen in half a second, so 1200 over 0.5 squared. And that's that. Part C, the diagram below shows some of the forces acting on a car. The car is accelerating at 0.5 meters per second squared. The car has a mass of 1600 kilograms, and the driving force on the car is 1000 newtons. Okay, so you can see here we have the driving force marked in. We've got some force that doesn't have a specific value, and it says calculate the resultant force acting on the car. So we have Newton's second law telling us that the resultant force F equals ma. We have the acceleration and the mass of the car, so it should be a simple job to get the resultant force. Okay, so we just fill in the mass. Remember, the mass is 1600 kilograms and the acceleration is 0.5. And if we multiply those, we get 800 newtons. It says then calculate the frictional force on the car. So we should really represent the forces on the car in some kind of diagram here. So we have an object accelerating, we've got this driving force of 1000 newtons, we've got some resistance force, which is the friction, that we don't know, but we know that the resultant force is 800. So the resultant force in the direction of A here, which is the forward resultant force, is d minus r. And we already know that that equals 800 newtons from the F equals ma calculation. So r is going to be d minus 800. We take r to the right hand side and bring the 800 over. And so d minus 800 equals r. So 1000 minus 800 equals r, which means that r is 200 newtons. Question 2a. Wind turbines provide some of our energy needs. And then we're told that the kinetic energy of moving air is converted to kinetic energy of moving rotor blades. And this in turn is then converted to electrical energy by the generator. It says calculate the kinetic energy of 1 kilogram of air moving at 15 meters per second. Show clearly how you get your answer. So this will be just using our kinetic energy equation. And kinetic energy is a half times the mass times velocity squared. Okay, so a half times 1 kilogram times 15 squared. And that comes to 112.5 joules. After passing through the rotor blades, the velocity of 1 kilogram of air is reduced to 9 meters per second. However, only half of this loss of kinetic energy of the air is turned into kinetic energy of the moving rotor blades. So calculate the kinetic energy of the moving rotor blades. So we have an old velocity of 15, a new velocity of 9. We already know the kinetic energy of the 15 meters per second value. We now need to know the kinetic energy of the 9. And that gives us a value of 40.5 joules. So that's the new kinetic energy. We had previously a value of 112.5, so we need to work out this loss. And that's going to be the old value minus the new value, which means that we're talking 112.5 minus 40.5. And that comes to 70 joules. So the energy in the rotor blades is a half of this. So the kinetic energy belonging to the rotor is a half times the loss of wind kinetic energy, which is a half times 72, which is 36. So it all comes down to paying attention to the stuff that they put in bold type. Half of this loss, so we need to work out the loss first, and then work out half of this loss to get the thing we're interested in. Part 3. The overall efficiency of a wind turbine is 0.3. For every 1000 joules of kinetic energy from the moving air, calculate the useful electrical output energy of the wind turbine. So we know that efficiency is useful output over total input. So the useful output is going to be the efficiency times the total input. So we've got 0.3 of an efficiency times 1000 joules of input wind energy, which gives us 300 joules of output. Part B. The efficiency of the wind turbine depends on the ratio of the speed of the air after it has passed through the rotor blades to the speed of the air before it passes through the rotor blades. So we've got these figures of before and after speeds. The graph below shows how the efficiency of the wind turbine depends on the ratio of these two speeds. So they're showing us a graph linking the ratio of these two values. And it says, what is the maximum efficiency? So when does the efficiency reach a peak? And I would suggest it's reaching a peak about here. And you can see that is almost corresponding to a value of 0.52 just here. And remember, efficiency doesn't have units because it's a ratio of two things with the same unit, and therefore they cancel. So the second thing we're asked about is the speed ratio. Which is this bottom axis. We need to find out the corresponding value there. And hopefully you can see that that is corresponding to a value here of about 0.3. So maximum efficiency of about 0.52, speed ratio where the peak happens of 0.3. Part 2. Describe the motion of the air after it has passed through the rotor blades of the turbine if the speed ratio, speed after over speed before, equals 0. Okay, so if the speed after over the speed before equals 0, then the top line needs to be 0. And if the speed after is 0, then the air must have stopped. Okay, so we can say that the air has stopped after going through the blades. Part 3 then, a wind turbine does not produce any electrical power until the wind speed reaches a value called the cut-in speed. As the wind speed increases, so does the output power until a particular wind speed is reached, after which the output power remains constant. However, if wind speed exceeds a value known as the cut-off speed, the rotation of the wind turbine is stopped to prevent damage, and the power output as a result falls to 0. On the axes below, sketch how the output power varies with wind speed, and on your graph mark and label the cut-in and cut-off speeds. Now, the important features of this are going to be that you mark in the cut-in speed and the cut-off speed, and the fact that it reaches a maximum at some point and stays that way until it cuts off. The fact that it's a curve here is really just a guess, because kinetic energy is proportional to v squared. You could just as easily have drawn a straight bit. But cut in, cut off, reaching a max value and staying at that max value for a period of time until it reaches the wind speed where it has to be shut off. So these 4 points are important. How you get from here to here is not really massively important, as long as you do have a value that increases. Part C, the photograph shows the type of weightlifting machine found in most gyms, and it explains that the user pulls down and at the same time then the weights move up. Describe in detail how this machine could be used to measure the personal power of a person using it. In your answer, you should state the measurements to take and the calculations needed to find the personal power of the person using the machine. So obviously they're going to do a certain amount of work in each pull, which will be based on how far the machine moves down. So there'll be a certain amount of distance here. That's an important part. There'll be a certain amount of force here on these weights, and the work is going to be F times D, so we need to know how many newtons they're pulling, or mass times gravity will give us F as well. So the idea is that they will do so many repetitions, and there'll be an F times D for each one of those repetitions. So we need to count out how many repetitions they can do in a set amount of time. So you might say we're going to give you a minute, or we'll time how long it takes for you to do 20 repetitions or something like that. So you need a stopwatch. You'll need to read off the mass and convert it to do either F times D or mgh to get your work. Multiply that by the repetitions. Okay, so your reps times your work, or potential energy gained by the weights, will give you the total amount of energy converted, and then you're going to divide that by the time you get from your little stopwatch. So the stopwatch is there to allow you to include time, which is what we need in order to find personal power. Okay, so we're going to need to count how many repetitions they've done. We're going to need to time that. That'll give us a time for all these repetitions to be done. So the work in each one is going to be this stuff here. The repetitions then will tell us the total amount of work done, and the time will tell us how long it took. So you need then to do powers, work over time, and calculate the person's individual power. It's all about measurements, instruments, and method. 3A then. Write down in words, in bold type, the formula used to calculate the density of a substance. Well, that's density is mass over volume. And it says also give the unit for density. Well, the most easy unit would be the standard unit of mass over the standard unit of volume. So I would put in kilograms per cubic meter. You could have any mass unit over any volume unit, but it would make more sense for it to be kilograms per cubic meter, since they're both standard units in their own right. Maureen is asked to measure the volume of plastic used in a small bottle, as shown below. She's given a large measuring cylinder and a supply of water. Describe how she could find the volume of the inside of the bottle. Well, the most obvious way to do that would be to fill the bottle to the brim with water and pour that out into the cylinder and see how much you've got. So that's probably the easiest method. The bottle is now filled with sand and the top is replaced. The bottle will now sink in the water. The large measuring cylinder is now half filled with water. Describe how she could find the total volume of the bottle. Well, this is the displacement method, so you're going to be lowering this bottle in, and once you lower the bottle in, then it should be possible to find the change in the readings here. So you have the reading you've got now, the reading you get after you lower the bottle in, and the difference between these two readings is the volume of the bottle. Okay. So you need to write a very short method explaining that you read the cylinder now before you put the bottle in, record that value, you read it again after you've put the bottle in and record that value. You then find the difference between the before and after so that you can figure out the volume of the bottle itself. What calculation does she need to make to find the volume of the plastic used to make the bottle? Remember, we had a reading for the inside volume. The displacement method with the measuring cylinder gave us the outside volume. So we've got an internal and an external volume. Well, the difference between the internal and the external volume will be the extra bit of plastic around the internal that makes the external volume. So the volume of plastic is going to be the external volume minus the internal volume. So basically, the reading coming from part 2 minus the reading coming from part 1. Part C then is the density of steam greater than, smaller than, or equal to the density of water at room temperature. Now this is ridiculously easy because clearly water is much more dense than steam, so steam must have a lower density than that of water. And part 2 then is use the kinetic energy to explain briefly your answer to part 1. And this is the idea that particles in a gas are much further apart and moving much faster. But density wise, the only thing we're interested in is how far apart they are. And they are quite keen on you using terms like molecules. In the case of water, it is a molecule. Remember, it's H2O. Rather than specifically just talking about particles. So in this case we would want to say molecules far apart in steam and close together in water. D. The graph below shows how the weight of an object varies with its mass on the surface of the moon. So we've got weight proportional to mass, as we would expect. It says, using the graph and your knowledge, find the difference between the weight of an object of mass 5 kilograms on the Earth and on the Moon. So we can straight away look at 5 kilograms here and look and find that we get 8 newtons corresponding to 5 kilograms on the Moon. Okay, so we can record the value belonging to the Moon as 8 newtons. However, on the Earth we need to do W equals mg because we don't have a graph for the Earth. A mass of 5 kilograms times g, we take g to be 10. So we get 50 newtons for the Earth, and the difference then is going to be 42 newtons. So I've just used delta W here, don't worry about that. The difference in the weight, you can just write that in words, is 50 minus 8, which gives us 42. And so our answer is 42 newtons. So part 2, on the planet Mars, an object that's 1 kilogram is 3.7 newtons. Draw the graph that corresponds to that. Okay, so we need to go to 1 kilogram and find 3.7 newtons, which is going to be about there. And then we need a straight line with a ruler that's going through that point. And it must also go through 0, 0. Obviously on the iPad it's hard for me to do it accurately, but you can obviously take much more time and do it very accurately. For Part A, Mary is the front seat passenger in a car involved in a road traffic accident. How might wearing a car seat belt reduce the injuries to Mary? So it says she's in the front seat, so she's in danger of hitting the dashboard and the windscreen. It does say she's the passenger, so she's not in danger of hitting the steering wheel. But anything that will keep her from hitting those hard objects will reduce her injuries dramatically. So you're really explaining that hitting the windscreen would require a short time to stop her, and being slowed by the seatbelt takes a much longer time, and that the bigger the time is, the smaller the forces on her. So we have a long stopping time that produces smaller forces and reduces her injury. State one other safety feature of a modern car which might reduce the injuries to passengers involved in a road traffic accident. So you're looking at things there like front crumple zones on the bonnet, things like airbags that might also help to reduce injuries by basically extending the time of the collision and reducing the forces. Mary has a mass of 48 kilograms, and at the time of the collision the car was travelling at 15 meters per second. Calculate Mary's momentum at the time of the collision. Well, momentum P is mass times velocity, so we need to fill in that mass and that velocity. And so that gives us a value of 720, and that will be in kilogram meter per second. Part B, Jane carries out an investigation on the factors which control the size of the centripetal force. She uses the apparatus below, and you can see there's a glass tube with a nylon thread. It runs out to a rubber bung, and at the bottom we have a force meter measuring the force on the thread. Jane holds the glass tube in her hand and whirls the rubber bung above her head. When the bung is moving at a constant speed, she records the reading on the force meter. For different values of F, Jane's friend measures the speed of the bung, V, as it is whirled round above her head in a circle. The radius of the circle and the mass of the bung remain constant throughout. The results of Jane's experiment are shown below. So we've got radius staying the same, we've got the mass of the bung staying the same, so the only thing we're changing here is V. And so we've got centripetal force values there, values of V, and then an uncompleted table of V squareds. So we have to complete this table entering the values of V squared correct to one decimal place. So we just go through them, squaring these velocity values until we get these V squared values. Part 2, on the grid below, plot the graph of F against V squared. You will need to label the horizontal axis carefully and select a suitable scale. So we've got force values going from 0 to 2 newtons, and our V squareds go up to 3.6. Sorry, 3.2. So we could go 0, 1, 2 for our forces in newtons, and just have 3 little squares to equal 0.1. And we need to go to 3.2 in the other direction here. So probably just go 1, 2, 3, 4 for our V squareds. And we just need to recognize that when we square velocity, we get meter squared per second squared when we're putting that unit in. So 0, 0 here is a point. There is also a point at 0.5 and 0.8, which is about here. There's another point at 1 Newton and 1.7. There's another point at 1.5, 2.6. And then we just plot the top point and put a line of best fit through those points. Jane's teacher tells her that the mathematical equation linking f and v squared is that f is k v squared, where k is a constant. Calculate the gradient of the graph. So there's a reason why they're doing this, because the gradient is going to be related to the f versus v squared graph, because this is in the form of y equals mx. The thing plotted on the y-axis is that. The thing plotted on the x-axis is v squared. So k must be the gradient of this line. That's why they're asking you to find it. So if you think about the line that we had, it went up 2 newtons whilst going along 3.2. So the gradient's going to be 2 over 3.2. And that gives us about 0.625. And it says, how is the gradient related to the value of k? And you just say that gradient equals k. Okay. Diagram below represents a window cleaner carrying a ladder and a bucket with the water cloths in it. The ladder is uniform, 4 meters long, and weighs 200 newtons. And you can see he has got its shoulder 1.5 meters from the end. So it's 4 meters all the way across here. We should probably put that information on the diagram. This is the bucket and its contents weigh 80 newtons. Clearly label with the letter P the position of the pivot. Well, the pivot in this case is his shoulder. So P is right at his shoulder. Mark clearly with the letter G the position of the centre of gravity of the ladder. Well, we need to find the middle of this ladder because it says it's a uniform ladder. Well, it doesn't. Oh, it does actually. Sorry, it does say it's uniform. So if we count how many bits we've got holes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 11 means that there'll be 5 of these either side, and there'll be 1 in the middle. 1, 2, 3, 4, 5. So the centre of gravity will be in this middle one here, and that's where we should be writing our G. So it says calculate how far from end X the ladder of the bucket should be hung for the ladder to remain balanced. So what we've got here is an 80 Newton downward force here. We've got the weight of the ladder, which is going to act from the centre of gravity, and that's 200 newtons. We've got the pivot here, and we know that this must be in the middle, so this must be 2 meters, which means that G from the pivot must be 0.5 of a meter. That's the one we're interested in. Okay, so we've got 200 acting down 0.5 from the pivot, and we've got 80 acting some unknown distance here from the pivot, which we will mark in as D. And we'll also mark in this distance here as A. And the reason we're calling it A is because that's the answer. That's the one they want. Now we need D for the moments problem, but we need A for the answer. It's vitally important in this kind of question that you redraw it as a simple moments problem. So what we have is his shoulder and 80 newtons here at a distance D, and 200 newtons here at a distance of 0.5 meters. Okay, so we now have a very simple moments problem to solve. And clockwise moments equal anti-clockwise moments, so 80 times d equals 200 times 0.5. So I'll just move down a little bit. So the anti-clockwise moment about P equals a clockwise moment. The anti-clockwise is 200 times 0.5 and the clockwise is 80 times d. And that means that d equals 200 times 0.5 over 80. And that equals 1.25 meters. But we should remind ourselves that d is not our answer, a is our answer. So d plus a equals 1.5. And that means that a equals 1.5 minus d, which is 1.5 minus 1.25, which is 0.25 of a meter. The window cleaner replaces the ladder with another type of the same length, but weight 220 newtons. In what direction would the bucket have to be moved to maintain equilibrium? Okay, so if we now have 220 at a distance of 0.5 of a meter from his shoulder, then that creates more anti-clockwise moment, and as a result of that, the clockwise moment on the other side would have to increase, so we would have to move the bucket further out towards the end. So towards the end or to the right would be the correct direction, and the explanation is that the heavier ladder will create more anti-clockwise moment, and so the bucket is needed to create more clockwise. Part B, the picture shows a Bunsen burner similar to those found in many school laboratories. Describe in detail how its design contributes to its stability and why this is very necessary. Okay, so we're talking about the stability of this object. So the pair of important ones that you remember: for good stability, an object should have a wide base and a low centre of gravity. So this has both of those because a lot of the mass is at the bottom there. And you need to explain that if it was to fall over easily, that would produce a fire risk or the risk of injury to the person using it. So just a good, well explained set of facts there. Question 6. The diagram below represents a neutral atom of an isotope of the chemical element helium. Carefully label the particles with their names in the spaces provided. So this is straight book work, adding in the particles. Now they've chosen an isotope with an odd number of nucleons here. So we're talking helium, which is the second simplest material in the universe. So these two must be the protons, giving it number 2 in the periodic table. The other particle there in the nucleus must be the neutron. And obviously around the outside we have electrons. Normal helium nuclei are represented by the symbol 42He. Complete the diagram to show the correct symbol for the nucleus shown above. Okay, so the one shown above has 3 nucleons and 2 of them are protons. So remember, that's what these numbers represent. 4 total nucleons, 2 is the proton number. So this would be 3 and 2. Part B then. Oh, sorry. If our government is to meet its carbon emissions target to help the reduction of global warming, it has been suggested that more nuclear power stations should be built. What is the name of the process used in today's nuclear power stations to produce energy? So that's straight book work of fission. Part 2. There is much debate as to whether more nuclear power stations should be built. Suppose the government was to suggest building one station in Northern Ireland. Would you be in favour of this? Circle your answer yes or no. And it says, explain your choice with 2 reasons, not including global warming, which means we're not allowed to talk about the fact that there's no CO2. So if you pick yes, then you're talking in terms of positive things like employment of skilled people, and the idea that it'll use a lot less fossil fuels, reduce our burden of use of fossil fuels. You can mention that there's no sulfur dioxide, that you won't get acid rain and things like that because of it. And the idea that it's one of these kind of power stations that you can just put on, and that you don't have to wait like renewables we do for the sun to shine or the wind to blow, etc., etc. If you choose no, then you have to think about the dangers associated. For example, the idea that you could have radioactive material produced, danger of leakage, danger of problems with the reactor, danger of even a terrorist attack or something like that, damaging it. So there could be plenty of reasons why we would go on the other side, on the no side. And the cost of decommissioning a station like that when it's ended its useful life could be very, very negative. Okay. Part C, radioactivity is known as an ionizing radiation. What do you understand by this? Well, we know what ions are. Ions are atoms that have lost or gained electrons. So when we talk about ionizing radiation, we're talking about the ability to remove electrons from an atom. Part D, there are many uses to which radioactivity can be put. The diagram below represents a thickness control unit for the production of steel plate. Which type of emitter, alpha, beta or gamma, should the radioactive source be? And explain your choice. So you've probably seen this in your notes. We have the idea of something being fed in here, and these rollers are squeezing it down. It starts off thick and ends up thin, and so these rollers are being forced to squeeze it down to a certain thickness. And then this system here is controlling how much pressure there is in these rollers. So how much of the radiation is getting through is directly being fed to the pressure on the rollers. So it's having to go through what we're describing here as steel plate. So we're asking which kind of source will go through steel plate. So I can't imagine alpha and beta. Alpha definitely not, and beta very doubtful that it would go through any reasonable amount of steel plate. So it would have to be gamma. So you would explain that alphas and betas wouldn't be expected to make it through steel plate, only gammas would. Explain then how the pressure on the rollers can be controlled by the system to maintain a constant thickness. So obviously if the steel becomes too thick, the gammas getting through will fall, and if the steel becomes too thin, the gammas will go over a certain amount. So basically, if the gamma reading becomes too high, then reduce the pressure on the rollers, and if the gamma reading becomes too low, then the metal's too thick, you increase the pressure on the rollers to squeeze it thinner. Part E, the chemical element carbon has an isotope C14, which is radioactive by beta emission. It is used in the process of radiocarbon dating to estimate the age of material that was once part of a living organism. C14 has a half-life of 5,600 years, and 1 milligram sample of oak wood removed from a living tree has a count rate of 20, and due to the presence of C14, and a 1 milligram sample of oak from an ancient dugout canoe has a count rate of 5 counts per second due to the presence of C14 that remains in it. Use the above information to calculate the age of the canoe. So this value here represents fresh wood, and this value of 5 represents old wood. So what we're sort of using, the modern value for the fresh wood is like what the canoe would have been at the beginning. And then what happens is that'll go through a half-life, another half-life, and reach this other value. So you've got one half-life and then another half-life to reach the final value of the dugout canoe. So the fresh value, the fresh wood from today, the living tree, is what the wood in the canoe would have had in it, 20 counts per second, and now only has 5 counts per second. So we've gone through 2 half-lives. 2 half-lives is 2 times 5600, which is 11200 years. And that's that. Okay, thanks for watching.